Hey guys, today we are going to be getting into energy, heat, work, and enthalpy. This is going to be topic 2, thermochemistry. Starting things off, what we want to do is we want to talk about just what is energy. One definition that we can use is energy is the ability to do work or to produce heat. Internal energy is the energy that we have in all the different forms, so potential and kinetic energy of a system. So we have to define what is the system, we have to define what potential energy is and kinetic energy is, and we'll get to that here. So first off, potential. Potential energy is energy because of the position of an object. Okay, so in physics, we think of this as, let's say you have a ball at a height. Well, that ball, even though it's not moving, has energy, because if it was released, it would fall. That potential energy would be converted into motion. In chemistry, most of the time when we're thinking of potential energy, we're thinking of energy stored in bonds that can be released as bonds are broken. Now, whenever you have bonded atoms and they separate, what you have to think about is this. So that you have your atoms and they're together and they're stable when they're together. You have to add energy in order to separate those two. So an increase in energy is what causes that separation. So in this visual, you can see right here, you have an ideal peak potential energy position right down at the bottom. If the molecules are too close together, then they have repulsions happening, pushing the two nuclei apart. If they're too far apart, then you have an attraction. But when they're at the ideal distance, you'll have that kind of sweet spot of potential energy. So you'll have more and more potential energy in an ideal stable condition. When molecules are far apart, they're going to have less of that energy overall. Now, secondary idea. When atoms come together, again, when atoms are bonding, now they start at high potential energy positions. As they come together, their overall potential energy is decreased. So again, this low value that you see, a low potential energy, and that is higher stability. So in that process, they would be giving off energy. Now, we referred to this earlier, but kinetic energy is the energy of motion, and there are a variety of different motion types. We have talked about translational motion, and translational motion is you have a particle and it moves along in a straight line like a bullet. Then we have rotational motion, and that would be, again, you have an object and it's rotating or spinning in space. And then lastly, you have vibrational motion, and that vibrational motion is when you have an object that is, again, vibrating, jiggling back and forth. Now, all of these motion forms refer to kinetic energy. And in different states of matter, you can see that. The vibrational energy, we always see that when we're looking at solids because they're locked in place, they're fixed. The rotational motion we see in liquids, as well as some vibrational motions. And then finally, with gases, that's where we start to see that translational motion. The kinetic energy is proportional to the temperature of our sample, okay? And there are a few different things that we can look at to help us understand what's going on here. So, starting it off, what we're going to do is we're going to look at a more in-depth view of this same potential energy diagram. So, we have our two nuclei, and you'll notice that we're graphing their energy position right here. So, if we have this nucleus and we draw it apart, you'll notice the energy profile increases. It's a higher potential energy. If you bring them together, they have this ideal position, and if you get them too close, there's a strong repulsion between the two nuclei. Okay, so it's important that we understand that concept as we go through it. Now, if we look at the forces, specific forces, you can see that we have a total force. It's really small in this case, but if I switch it to some other atoms, let's say argon, as I drag these apart, you'll see we have some attractive forces that get stronger as they get close together, But then once they get together, these strong repulsive forces are going to take hold. We can split that up into both attractive and repulsive forces, and you'll notice that as they get closer and further apart, there's going to be this stability. We increase the attractive forces, but we also increase repulsive forces, and they need to be balanced in order for it to be stable. So the arrows have to be identical, they have to be same length. So the next thing is, let's talk about, remember, the effect of temperature on motion. So we've seen that there are these three motion types. What we want to do is we want to look at what would happen if I were to go ahead and add heat, add energy to this current system. So at present we have our solid phase, we have neon, and you notice that the molecules, they're jiggling, they're just in this vibration. But if I add heat, I can get them to kind of shift and slide around a little bit. And so now they're not as locked in place as they were previously. If I keep adding energy, we continue that same process, and if I get enough energy added, some of those particles will actually escape the attractions between those particles. So we're seeing this clump in the middle. We'd expect that would be more of the liquid state, but there are a few particles that have shifted apart. Those are going to be in the gas state. All right, the next idea that we have to get into is the idea of energy conservation. Energy is never ever created or destroyed. So this law is similar to one that we already know, the law of conservation of matter. Matter can neither be created nor destroyed by any physical or chemical means. Well, keeping this in mind, energy is a little bit different in the way that it functions. The energy can be used to modify a system, so it can change some sort of a system, but any changes are going to be balanced. So if a system gains energy, it means that the surroundings must have lost energy, and vice versa. If we have a system, so we'll call this my system, and that system is divided by some boundary. Outside the boundary, we have what we call the surroundings. Now, if energy leaves the system, the exact amount of energy that leaves the system is gained by the surroundings. So energy isn't created or destroyed, but it can be transferred back and forth. Another idea is that energy can change form, but that doesn't mean that it's been destroyed. So remember our previous example where we talked about having a ball at a height. Well, initially, it has just pure potential energy. So it's 100% potential energy. Well, as we release the ball and as it comes towards the ground, some of that energy is translated from potential into kinetic. It begins moving. So halfway down, what we have is 50% potential and now 50% kinetic. But if you add those two up, you're going to get up to your 100%, the original potential energy. And when this ball continues and it falls and makes its way all the way down to the ground, at that moment, it's going to be 100% kinetic energy and 0 potential. But again, the total amount of energy from the start to the end is always going to be the same. Now, one key thing that you should just pay attention to is that this law, the law of conservation of energy, is also known as the first law of thermodynamics. There are 3 thermodynamic laws, and really, heat is that study of, or the study of heat is thermodynamics. Now, what we want to do is we want to define a few specific terms. We talk about heat, and heat is often very confused. Heat is not the temperature, how hot something is. Heat actually is when 2 different systems that have different temperatures are touching, are in contact with each other. Now, when they're in contact, what will always happen is energy will be transferred from the higher to the lower energy source. We call the quantity of energy exchange heat, and this flow idea is very, very, very important. So once again, if I have 2 objects, and these 2 objects are in thermal contact with each other, the object that is hotter is going to transfer its energy to the thing that is colder. So for us, once again, it's just important to understand that there will be a transfer of energy, and that transfer of energy is always going from the hotter to the colder. The total amount of energy change is called heat. Temperature, we've mentioned already, it's a measure of average kinetic energy, but we should be a little bit more specific. When we say kinetic energy, what we're thinking about here is the mass of a particle and the speed of a particle. That's how we can determine the kinetic energy. In fact, our formula that we'll use is the kinetic energy is equal to 1/2 times the mass of that object times the velocity of the object, the speed, squared. Right? So kinetic energy, 1/2 mass times velocity squared. The average kinetic energy of all the particles within a sample is what we record as the temperature of the sample. So a few additional just thermodynamics terms that you should know. We've already mentioned the system, but let's be explicit. The system is the part of the universe that we're focused on. It's the experiment, the solution, whatever the thing that we're focused on is. And everything outside of those surroundings, outside of the system, is known as the surroundings. Most of the time, when we're considering the immediate surroundings, that is where the transfer of energy is going to go to. It's in thermal contact with the system. So endothermic is one way that we describe a process. Endothermic, you can think of it like this. It is taking in energy, It is the absorption of that energy. It's a heat exchange process again. And so energy goes into the system. In an equation, we would write this as energy is a reactant, so it's written on the left side of that equation. You can think of it in terms of the way that you perceive it. If you were to touch an object that is absorbing energy, it takes energy from you, out of your hand, and it feels cold to the touch. In enthalpy terms, which we'll talk about in a second, we see that there is a positive change in enthalpy, the delta H value. Now, if we have absorbing energy, we also can have systems that give off energy, they release energy. So exothermic is when energy is exiting, it is going out of a system. That's our release of energy. Energy in an equation would be written as our product. And you can think of some of these reactions like if you start a fire, a combustion reaction will generally give away energy. And if you stick your hand in a fire, your hand gets burned. It feels very hot to the touch. So again, it's that same concept. You can think about how you perceive it, and that'll help you understand whether energy is going in or going out of a system. In enthalpy terms, there is a negative change in enthalpy for these reactions. Well, we've referenced it here, but now I guess we should be explicit. Enthalpy, which is given the sign H, enthalpy describes the flow of energy. Now, there are a couple things that we have to keep in mind with this energy flow. Okay, we've talked about energy flow being heat, and enthalpy is heat. However, it's the heat of a specific process. It is the amount of energy per mole of something taking place. So changing 1 mole of ice into liquid water would be an enthalpy, a specific enthalpy value. And it always has to happen under some standard conditions. So let's explore enthalpy a little bit more. There are a few specific enthalpy terms we need to be really familiar with. The first is the enthalpy of reaction. So this is when a chemical change occurs, any kind of chemical reaction. You can either absorb or you can release energy in that reaction. The units of enthalpy will always be constant, kilojoules per mole. Now, you may see referenced in some previously issued texts that enthalpy is just kilojoules, but that's a little bit too limited. Remember that this is the energy of a specific process, so there is an amount that has to go with an enthalpy value. So in this case, it is per mole of the reaction taking place, and that might be the product forming if it has a coefficient of 1. If it doesn't, then you need to reduce everything so that it can be a coefficient of 1. Well, in this one example, you'll notice that the reactants have less energy than the products. So this means we had a positive delta H, and that means this is an endothermic process. This process on the right, you'll notice that we have a negative delta H. So the enthalpy change for this reaction is negative. It gives off heat, gives off energy. Now, another feature that you'll notice on these diagrams, these are known as reaction pathways. In every case, there must be some energy gained in order for these things to exist, to happen, for a reaction to take place. So there has to be some energy added, no matter what, in order for the reaction to take place. We refer to that as the activation energy of a reaction. Now, we've looked at general reaction enthalpies. Now let's focus on some specific reaction enthalpies. One of our specifics is for combustion. We should already be familiar with combustion. We've done combustion analysis problems, and now we are going to be very specific in looking at a combustion reaction. Features of a combustion reaction are we typically react with oxygen, and another thing is you always need 1 mole of the substance being burned, just 1 mole of the thing being burned. This visual example, we see that we have 1 CH4, 1 methane molecule that's burning an oxygen. It produces carbon dioxide and water, but we don't necessarily have to form a hydrocarbon. Combustion can be anything combining with oxygen. Now, formation is our second type, and again, this is a specific subtype of a reaction. The formation equation is formation of 1 mole of a specific product from its standard elements in their standard states. Like any other enthalpy, it is going to be represented as kilojoules per mole of that reaction. The example that we have here is actually a formation equation, but also a combustion. If you look at it, you notice that we are forming 2 H2O gases. Well, 2 H2O, that's a problem here, right? We're supposed to have 1 mole of a compound formed. So what we can do in this case, what's unique about these thermodynamics equations is we're actually able to have coefficients that aren't whole numbers. So I would reduce this by dividing by 2, and I would get 1 mole of water as a formed amount. It comes from 1/2 of an oxygen molecule, and it comes from a single hydrogen molecule. So it's got to be in those terms. It must have 1 product forming, just like a combustion reaction must have 1 of the burned item. So I made reference to this earlier, but let's be explicit now. Another enthalpy is known as the enthalpy of fusion, or the heat of fusion, and this is the amount of energy that it takes for 1 pure substance to go from its solid to its liquid form. Now, we always, again, express these with amounts in mind, so it's represented as kilojoules per mole. The contrast to that would be the enthalpy of vaporization, and this is turning 1 mole of a substance at its liquid state into its gas or vapor state. One other thing with this is these things only take place under certain conditions. Fusion will only occur at the melting point of that substance, so that is the temperature where it transitions between solid and liquid. The vaporization can only occur at the boiling point temperature, and this is, again, the transitional point between our liquid and our gas phase. All right, here are a few more thermodynamic terms that we should be familiar with. The first, we've already learned about the heat content of a system. Now we want to learn about the organization, the ordering of the system. What we do is we describe this as the entropy of a system. We give it the symbol S. And if we have a system that is highly ordered, very, very organized, like a solid, we would say that it has a very low entropy. It's not dispersed very much. If I take that solid and I change it, I break it apart, I am making it more disordered, so I'm increasing dispersal, I'm increasing entropy. So that, again, a solid would have a very low entropy value. Okay. Has a very low entropy value. And then we have our broken apart, our separated liquid or a gas form. That is going to have a high entropy. So this process goes from low entropy to high entropy, this is going to have a positive change in entropy. Next, we're going to learn about another thermodynamic quantity, and that is Gibbs free energy. Gibbs free energy is a way of determining whether a process is favorable in terms of overall energy. And it takes into account both the entropy and the enthalpy, as well as the temperature conditions of a system. Gibbs free energy, the change in that Gibbs free energy, is going to be equal to the change in our enthalpy minus the temperature times the entropy change. So delta G, delta H minus T delta S. And again, we want to use this to predict whether or not a specific process can happen. So under certain conditions, we see that a process is favorable or unfavorable. Now, in the past, we've used the word spontaneous to describe thermodynamic favorability. The AP now, the College Board, they want us to really stick with this term that it's thermodynamically favorable, okay? But in your head, if you want to continue thinking that, oh, it'll happen, it's spontaneous. It won't happen, it's non-spontaneous. It doesn't happen under all conditions. So whenever we have a delta G value that is negative, it means that we have a spontaneous or thermodynamically favorable process. If we calculate out a delta G to be positive, that means that it is a non-favorable process. So if we look at the conditions, if we have enthalpy values that are very, very low or negative actually, that agrees with nature that that's going to be getting into a situation where we're increasing the stability of the system and it gives off energy. When our entropy term increases, and that's a positive change in entropy, that also agrees with nature. The overall disorder in the universe is increasing over time. So under these two conditions, if you have a negative delta H and a positive delta S, then a process is spontaneous under all conditions. If you reverse that, you have positive delta H with negative delta S, that will be non-spontaneous under all conditions of temperature. For the other two ideas, look at the enthalpy term to be your focus. If we have a positive delta H, it is only going to be spontaneous when it has a high temperature. So in that case, once again, if we have an entropy value that is positive and an enthalpy that is also positive, the only way for this to be possible, for this to happen, is if the T delta S term is greater in its negativeness than the delta H term. And the opposite is true when I have processes that are driven by enthalpy. If I have a negative delta H value, the only way that that can be spontaneous is at very low temperatures. So we'll go back to that, but again, have a basic understanding of Gibbs free energy. It is our way to predict whether or not a reaction will take place. Thermodynamics, we've been using this word thermodynamics, but we should probably formally give it to you as the study of energy and conversions between energy and other simple physical quantities like pressure, temperature. Work is a term that we need to be very familiar with as well. And work in physics is very, very specific. Work in physics is when you apply a force to an object and cause that object to move. Right? So if you look at this example, you'll see that we have a force that is pushing this object to the right. The object does move to the right, so work is being done. In terms of directionality, it's really important that we pay attention to that in physics. Now, for us, chemistry, directionality is not as important. For us, really, we're dealing with this idea of gases and gases being transformed. For us, we're going to define work for gases as the negative pressure times the change in volume. So looking at this ball, let's assume that it is a hollow ball, though in reality golf balls have a particulate substance on the inside. Imagine it's a tennis ball, for example. Okay, now that is completely filled with air. Well, what will happen is as you apply a force on one side of the container, the ball itself, it deforms the ball. It makes it change its shape. And in the process, it is causing the gas to take less space. So that's a compression. Compressing it decreases the overall volume by applying the pressure. So work can be thought of in those terms as well. And we'll get back to that definition of work a little bit later. One thing to keep in mind whenever we're dealing with thermodynamics, though, is this idea also. We've talked about standard conditions before. And when we discuss STP, standard conditions of temperature and pressure, that occurs at 0 Celsius. However, standard lab conditions, we don't work in freezing conditions. 0 degrees Celsius is where water freezes. So we change our standard lab conditions to be at 25 Celsius. And when we're dealing with gases, we want to maintain that they have a constant 1 atmosphere of pressure, and any solutions we use would have a 1 molar concentration. The way that we can express that we're looking at a quantity in standard conditions is by adding our degree symbol to the end. So a standard enthalpy would be written as delta H with that degree symbol. Standard enthalpy, or entropy term, I should say, would be delta S with the degree, and standard Gibbs free energy would have that degree symbol as well. Now, we've mentioned that energy and work, these are synonymous terms, right? So energy and work, energy is the ability to do work. Well, work can also produce heat. So these are two sides to the same coin. The overall energy change, or the internal energy of a system, is a combination of its heat and work. So if we have a process where heat is absorbed, we say that's a positive Q value. Heat is absorbed, it is going to increase potential energy. Now, in this visual, we're seeing that the surroundings are adding energy to the system. So we're increasing our heat content. If we have the opposite situation, if our system is going to give away energy to the surroundings, that's where we see this decrease in potential energy. So that's the heat component. Now let's talk about the work side. If work is done on a system, it's a positive sign of work. Okay, the system has work done on it. In our understanding of gases, that's typically how we're looking at this. Then it's compression of a gas is work done on the system. And work done by the system is when our container expands. We're doing work on our container, and that is going to be a negative sign on the work. So our visual that we look at, notice that we have an initial state where we have a pressure that is pushing down on our system. The final state shows that our overall gas sample is larger. So this is an expansion. The area of expansion is going to be the top part of this column, and then take an area times a height in terms of this cylinder. That's going to be a volume. So the change in height times the area gives us our overall change in volume. And as we said before, our definition of work for gases is going to be negative pressure times change in volume. That again is our work. Now, volume changes, that is going to be the chemistry perspective of work in most cases. You need to know a few of the units to be familiar with these things. A joule is our standard energy unit, and a joule is a derived unit from some other units. A joule is defined as 1 liter times a kilopascal of pressure. So again, we have our pressure term, and then we have our volume term here. So the change in P delta V gives us our joules. Well, you should also be familiar, because we use atmospheres in the lab a lot of the times, how to convert between atmospheres and kilopascals. There are 101.3 kilopascals in an atmosphere of pressure. So I'm going to give you an opportunity to work on these exercises on your own, and then you'll be able to check them. The answer for this is 17.0 kilojoules. You can check exercise 2 we are going to have 27.3 kilojoules. For exercise 3, there was a typo in your packet, but this is the true way you're going to convert between liter atmospheres and joules. Your final answer should come to 7.9 times 10 to the positive 7 joules. So we have discussed enthalpy. Now there are a few specifics about enthalpy that we want to talk about. Enthalpy change, the delta H value, it is called a state function. And a state function means that there is no difference in the way you get to a specific state. If I have a sample that is 50 milliliters of water and that is at 25 degrees Celsius, it doesn't matter how I got to that state, how I got to that condition. I might have started with 50 milliliters of water at 100 degrees Celsius and I cooled it down. I might have started with 50 milliliters of ice at negative 50 degrees and then heated it up. So it doesn't make any difference how I got to a specific state. All that matters is that the change occurred. Okay, so the path doesn't matter, it's just that a change can occur. Secondly, delta H, we said it's heat. It's heat at constant pressure, and it is in terms of the amount of energy per mole of a substance. There are several ways that we can find enthalpy. There are a lot of different ways, right? Because it's a state function, there could be multiple processes in place. Stoichiometry is one of the ways that we can figure this out. If we know the energy of a specific chemical reaction, well, I could calculate if 7 of these reactions take place, what's the total amount of energy? Calorimetry, which we're going to discuss in more depth later, this is the idea of comparing the heat transfer of one substance to another. You also could look up a table of standard values. Often you can find this information published either online or in a textbook, and then we can make comparisons with that. One of the prime ways of making those comparisons is with a technique called Hess's law, and we will go into Hess's law and how that works. And the final form that you should be familiar with is the idea of looking at bond energies. Since the potential energy is the energy stored in bonds, if we can look at all of the bonds that are formed and all the bonds that are broken, we can find the total amount of energy in that. So we've already seen this diagram. Again, a couple things to pay attention to is the difference between the products and reactants gives us the overall change in enthalpy. And please remember that for all chemical reactions, there is some energy required to kickstart the reaction. That is called the activation energy. So this is going to be your final piece, guys. You can work on this question on your own, but just to check. The first part, does the beaker get warmer or colder? It should get warmer, but you could justify that with some logic. Next, is the reaction endo or exothermic? It is going to be exothermic. If the beaker is getting warmer, it's gaining energy. And then finally, what is the enthalpy change for the dissolution? You're going to have to calculate this one out. You find it is negative 10.7 kilojoules per mole of reaction. All right, so hopefully that was helpful, guys. Make sure that you answer all the questions here, and we'll discuss this